Welcome and thank you for joining us today. My name is Brielle and I'm one of the organizers for this year's Quantitative Seminar series, and I'm a member of the Converse Lab. And I'll begin by acknowledging the Coast Salish peoples of this land, the land which touches the shared waters and tribes of all bands and tribes within the Suquamish, Tulalip, and Muckleshoot nations. We also acknowledge that we live and work on the ancestral lands of the Duwamish people, the first people of Seattle. So I'm very excited today to introduce our speaker, Nathan Hostetter, and he is currently an assistant unit leader of the USGS North Carolina Cooperative Fish and Wildlife Research Unit and assistant professor in the Department of Applied Ecology at North Carolina State University. Nathan's research focuses on the development of integrated modeling approaches to study the distribution and demographics of populations and address basic and applied conservation challenges across a variety of taxa, including mammals, birds, fish, and reptiles. Also, Nathan has been a great member of the Converse Lab working with us and has helped us with many modeling issues, and we're very thankful for Nathan to be a part of our lab, and we're excited that he has moved on to an awesome position. So thank you, Nathan, and you can take it away.
Great, thank you, Brielle. And thank you everybody for joining us today and being part of this talk that I'll be presenting on integrated agent harvest models, estimating abundance, demographic rates, and harvest of wildlife populations. As we go through this, please feel free to add the questions in the chat. It appears that's the way we'll handle it, and I'll go through the questions at the end. The work I'll be presenting today is still an ongoing research project that we're working on, so all feedback is greatly appreciated. Questions, comments, thoughts, I'd love to hear what people think of the approaches that we're using in this study. And so with that too, I'd like to first acknowledge the co-author, collaborators, and funding for this project. This has also been led by Dr. Sarah Converse there at the University of Washington with the co-op unit there. As Brielle had mentioned, I had actually initiated this. We had initiated this project while I was a postdoc working there. We've continued to work and collaborate on this now that I've moved over to North Carolina State University. We'd also like to acknowledge the Maine Department of Inland Fisheries and Wildlife, who is funding the study and directly collaborating on the studies, particularly Jen Sean, Craig McLaughlin, and Matt O'Neill, who have really been instrumental in getting this whole project off the ground. And also the other PI on this project, Angela Fuller, with the U.S. Geological Survey at the New York Cooperative Fish and Wildlife Research Unit. And also, I'll be presenting a bunch of results and data today from a long-term study that's been going on in the state of Maine. And so with that, all the contributions from the field technicians, the pilots, and the staff that have been going on here. And also a big thank you to all the members of the Converse Quantitative Conservation Lab. As we started on this, and I've been pestering folks about some of these challenges for years now as we worked on these approaches together. So a brief outline of our talk today. I'm going to start out with the idea of how we're looking at ways to be able to link age data to population dynamics in a very broad kind of sense, and then focus on our case study and spend a lot of time on that, where we develop an integrated agent harvest model for black bears in Maine, where we're looking at ways to estimate abundance, demographic rates, and age structure, and then also predict the population responses to future management actions, and then wrap up with some ideas of summaries there at the end. And I'll go through this about linking age data to population dynamics and this integrated agent harvest model. One of the really exciting things about presenting today for the SAFS groups also is that this integrated agent harvest model has a lot of long tradition in some of these fields of harvest management, but it's also really similar and shares a lot of similarities with things like catch at harvest or age at catch models and fisheries, integrated population models, specifically age or stage structures, integrated population models. So as I go through and keep mentioning this age at harvest model approach, I know different folks in the audience may be thinking about different ways that this fits together, but I think there's a lot of commonalities across both the fisheries and wildlife world in these ideas of how do you use age information from harvested or catch data to link back to population level processes. So with that being said, we can think about how we collect age data across a whole variety of different studies here. We use age information almost ubiquitously in wildlife and fisheries applications. We can think about lethal and non-lethal approaches that we get this information, so maybe from an otolith from a fish, from a harvested animal, or even from marking programs where we may mark juveniles or cubs that we find in dens. We could get measurements of age from non-lethally collected tooth samples or from scutes from turtles. There's a whole variety of ways that we can think about how this age information becomes important, and it's a fairly standard, straightforward metric that we generally collect when we're handling animals. There's also some really fun ways that we can think about age proxies that are increasingly being used to understand populations for this. So for instance, you can think about a nest monitoring study where maybe you're thinking about, instead of age of the individual, you're thinking of age in terms of the number of days that the nest has been there. And similarly, there's some really fun, exciting work from folks with the USGS out of Patuxent, where you're thinking about the duration of time individuals may spend at a stopover location. And so in that sense, although you're thinking about the number of days, you can see how that relates back to a kind of an age approach too, where in this sense, it's the number of days you spend at a stopover location or your age at that location. And so by thinking about these as a more broader concept, it kind of all links back this idea together of how we can incorporate this time and aging component into demographic modeling approaches. And so this has been a big focus of some of our research as our larger team over the past few years, because there's a lot of new opportunities then of ways we can think about integrating age data into research studies and monitoring programs. And this information from the age data can do several important things of understanding why we're collecting it and how we end up using it. And this includes things like improving parameter estimation. So if you can understand how populations age and change through time, you can actually better than sometimes estimate the underlying parameters of population growth rate, survival, or reproduction. But bigger than on that too is asking new ecological questions and identifying important hypotheses that we want to consider. So trying to better understand how aging or the age structure of the population is related to the drivers of the population dynamics. So there's things about age-specific survival or reproduction that are important when we're looking at whether populations are growing or declining. And similarly, this can be really important to inform conservation and management actions. We can think about age-structured harvest programs or age-at-catch information that can provide this information of thinking about what we need to do in terms of managing populations in the future and how the underlying age or age structure of the population are related to those topics. So with that brief introduction then, I kind of wanted to just jump right into the case study that I'll be talking about today, which is this integrated age-at-harvest model that we're building for a black bear research and management program in Maine. Again, this mentioned all the co-authors and collaborators there in the beginning. This has been a long-term data set that Maine has been collecting, where we're actually now trying to work together to understand some of the objectives of collecting this information through time. So in these discussions with the management agency, we kind of identified the important information needs that they've been collecting and are interested in understanding to help them better make scientifically informed management decisions. Specifically at the top level, they mentioned the need for statewide and regional abundance estimates of black bears in Maine. They need these estimates to both manage harvest and identify areas of possible conflicts. Underneath of that, then we want to understand what's driving population change across the state. And this included ideas of survival, reproduction, harvest estimates of black bears, again, across the entire state. And finally, we want to think about cost-effective research and monitoring program activities that we can think then of, if they're collecting statewide information at some levels, how can we also integrate smaller level research programs to develop a way that you can then inform objectives 1 and 2, your abundances and your survival, by these cost-effective research programs. So taking this as kind of saying these are the broad scale objectives that they were looking for, we wanted to then link them back to what were the actual metrics that we could estimate or model as part of this process to help them make these management decisions. And so keeping these 3 same objectives or information needs up here, we can then link them back to say, well, if you're thinking about statewide and regional abundances, and we started asking what was exactly needed, it was annual estimates. That's what they were primarily looking for out of the results here, an annual estimates of the statewide population, But also you can see here, this is the state of Maine shown on the left, that it's divided into 28 different management districts. And so you would also like to be able to estimate abundances at those different spatial scales, statewide and management districts. In terms of information needs then for survival, reproduction, and harvest, again, they were looking for annual estimates to see what's varying through time in this, and also how survival, reproduction, or harvest may be influenced by their actual management actions. And then when we talked about this information need of cost-effective research and monitoring programs, we were able to boil this down to really kind of outline what this meant. And this was looking for a way that we could predict future abundance under different management approaches. And so saying, well, what if the number of permit sales changed in the future? How would that affect population dynamics moving forward? But then also we wanted to think about some of the sensitivity to possible biases that are in these data sets that we're using to estimate statewide abundance. So for instance, if there's a change in reporting rates or uncertainty reporting rates, how much impact would that have on them making a decision about what's the most appropriate way moving forward? So with this kind of general framework in mind then, we started to think about the data that has been collected through the years, how we can link that data both at the statewide level where they're getting harvest information and these research study levels to kind of answer these questions. So what does the data look like for this population? Well, we've been using a data set that's been a long-term data set here in Maine from 2008 to 2020. We can think about the different spatial scales that the data are then collected at. We have this statewide information from the harvest data. So every fall, there's a harvest season for black bears in Maine. And as part of that, all bears that are harvested are supposed to be reported at a check station, which gives you then information on the number of bears that are harvested by sex and age class each year, where we had data from 2008 to 2019. And it also tells you the management district that the bear was harvested in. Then at a more local scale, we also had 3 long-term research and monitoring sites that Maine has been maintaining since 2008, and actually even some of these sites before then. These sites are Stuckwood Pond, Down East, and Bradford. And during these 3 study site locations, every winter they go out and they do annual den surveys. So this means that in January, February, March, they'll go out and they'll check these dens and they'll get in and they'll actually look and count and mark the number of cubs that are in there. So this gives you information of looking into the den and saying, does the female have cubs? And if she does, how many? And if those cubs are juveniles, or excuse me, cubs of the yearlings, then they'll actually get an ear tag also. Additionally, at these research sites, there's telemetry collared females, and they maintain somewhere between 40 to actually 90 bears across the entire 3 study sites that have collars on each year. And then finally, for the males and the females that don't have collars, they also get ear tags. So we have these long-term mark recapture data sets, known fate telemetry data sets from these 3 study sites, along with estimates of reproductive output, basically the proportion of females that have cubs and how many cubs they may have annually from each one of these 3 study sites. So with this in mind, we started talking to this group then about thinking of ways we could use all of these pieces of information to better estimate and address their information needs, particularly state and regional estimates of abundance and the demographic parameters that are driving changes in abundance. And this led us down the road of thinking about agent harvest models. And broadly, we can think about these agent harvest models as ways that we can analyze the sex, age, and harvest data to get estimates of abundance and how abundance is changing through time. Now, recently, too, there's been a big push in trying to think about ways we can integrate additional data sources into these agent harvest models, particularly studies coming from research studies looking at ways you can use these smaller scale research studies, quantify things like survival and reproduction that can be directly linked to broader scale studies on harvest information to give a more holistic and robust estimate of the population level processes. And so by bringing these research studies, local research studies together with these broader scale statewide estimates of harvest, it gives you the ability to jointly estimate abundance, the demographic processes, and harvest estimates across the state. So next I'm going to kind of walk through the general agent harvest model and some of the underlying ways that these things are connected through time. And again, thinking in the back of your head, if you're looking at this, and thinking this could apply across a whole variety of populations. It's exactly correct. Fisheries world, terrestrial world, we use a lot of these same ideas. And how this is really built then is you can think of an underlying process model that explains age-specific abundances and how abundance changes through time. And so for here, what you're seeing is the first year abundances, where we have some number of individuals, N of age A in year T. And so here you can have the number of age 0, or in our case, cubs in year 1, number of age 1 or yearlings in year 1, the whole way up to some oldest age class, which we'll mark with a large A, that says that's the absorbing age class of the oldest individuals. And so then summing across this row of information then would also give you the total number of individuals in the population in year 1. The population then moves on to year 2. And again, you still have the same age structure in year 2, but these estimates, or this abundance in year 2, is not an independent version of year 1. Instead, we can think about how the demographic rates link these 2 years of data. So for instance, then the number of age 1 individuals in year 2 is some function of survival between age 0 individuals the year before. And then up the whole way up to the oldest age class, where it's absorbing, where individuals transition into that age class, and the oldest individuals can also survive and remain in that age class. Further then, you can think about what leads to recruitment into this population then, or the number of new individuals that are entering as births, as some function of breeding age individuals. And so this can be varied depending on the population of interest, depending on which age classes actually produce offspring and the rate at which they produce offspring. And this is kind of the overall process model then. And you can just start to take that and repeat it for numerous years throughout the study, and just have this idea then that there's some underlying process model that explains the abundance of individuals by age class, and is linked through the demographic processes that lead to the aging of the population and the reproduction of the population, the reproductive numbers. So taking this then to an integrated age at harvest model, we were able to take this underlying process model and think about how the information that has been collected links to this underlying process model. And so with this, we could think about the statewide harvest data that we've been collecting in each of the management districts statewide, and that harvest information directly informs both the abundance, survival, reproduction, and harvest information from this. But there's no way that we can actually get all of these separate estimates from the harvest data alone. So instead, what we're able to do then is use the telemetry and mark recovery data from the ear tags and the collars to use an open population conditional on capture, survival, and harvest model then to estimate the parameters for survival and harvest. And this den survey data, where they go into the dens each spring, they count the number of cubs that are there, which can directly inform the reproductive process, saying what proportion of females have cubs and how many cubs might they have. So overall, the data that were available during our study period of 2008 to 2020 resulted in 670 marked females across the years, and 244 of which were harvested, 780 marked males at these 3 study sites, of which almost 300 were harvested, and over 35,000 individuals that were harvested across the state during 2008 to 2020, with about 20,000 males and 15,000 females. The age structure that was being recorded during all of these suggested that most of the bears were between about 0 and 8 years old. However, we did have this long tail with the occasional observation of bears that were over 20, and in one case, harvested bear that was estimated as 32 years old. And just for reference then, the harvest information that comes with the age data there is a tooth that's being submitted with harvested bears. One of the things I'll quickly draw your attention to, though, is that you will notice that of these number of marked individuals, the harvest probability is actually expected to be quite high. You can see that ratio, the number of harvested to the number of marked, suggesting that yes, indeed, harvest is probably a driving factor in this population just by looking at the marked data alone. So this is a quant seminar. I really wanted to jump in deep into some of the methods that we're using to model this population and really get into this. So hopefully we can get some good feedback and discussion going about how we can make some improvements, changes, suggestions to these approaches. So with the indexing that I'll be using in the subsequent slides to kind of work through this, we use A to denote age, where our age classes for this bear population are 0 being cubs, 1, 2, and up to a 10+ age class, which is our absorbing oldest age class. We then have the sex, both as males and females, denoted by lowercase s. We have our 28 management districts J. T denotes year, 2008 to 2020, and I is individual bear in the capture recapture sense. So going back to working with the state agency and saying what are the primary metrics of interest that we really want to tease apart from this model, the big one is the abundance. So that ASJT, excuse me, which is the number of age A, sex S bears in management district J in year T. And the other thing about this is that it may not always be this detailed that we want the information in. Instead, we want to sum across things like management districts to get statewide estimates, sum across sexes and age classes to get total estimate abundance. Then we have this non-harvest natural survival probability. So this PAST is the probability of surviving all natural mortality causes. And then we have a harvest probability, HAST, which is saying the probability that given you survive from the den season to the harvest season in the fall, what's the probability you're then harvested? So again, you can think about this non-harvest or natural survival probability being the probability you survive from January to right before harvest, and then this harvest probability being that conditional on surviving, you are then harvested during the harvest season. And we use this gamma AT as the probability of female in age class A has cubs. So what proportion of females are producing cubs that year, and then conditional on having cubs that year, F sub A is the expected cubs per breeding age, which we also allowed to vary by age class. And again, the primary sources of data that we're going to be talking about today are harvest information, which is again by age, sex, management district, and year. Our capture recapture data, which here we're denoting as YIT, and then our counts of cubs per female per year. And so this is how we start then kind of bringing all of these things together. So I'm going to first describe the underlying process model about the abundance across space and time, and then how we link these pieces of information back to that underlying process model. So again, abundance in year one. We're going to have some abundance of age class A, males and females in each of the management districts in year one. We assume that's a Poisson random variable with some mean rate lambda, where we allow lambda to be a function of both the age and the sex, and an offset for the area of each of the management districts, and some randomly distributed, normally distributed random effect that's specific to each sex and age class. So a way to kind of think about this is that that's the beginning population in the first year, has some distribution across space. And the way we formatted this is this does not enforce any kind of stable age structure or any underlying age structure. It allows it to be estimated from the data. By having this offset here, it allows this beta estimate to be a log scale average density in year one. But each management district can vary in the number of bears that it has in it, or the underlying average density, due to both the area of the management district, but then also this random effect that allows it to increase or decrease. Then the question becomes for the process model, well, the abundances in subsequent years are not independent any longer. Instead, they're this transition process of aging and survival. And so our underlying process model that we can think about here, shown in the bottom left, is saying that the abundance of the next age class in the next year is actually then a function of the previous year's abundance in the lower age class that survived all non-harvest mortality and were not harvested. And so these arrows going across here saying that the number of 1-year-olds can become 2 if that age class specific survival and were not harvested in those years. So then we allowed survival also to be age class specific, where we grouped ages into 0, 1, 2, 3 to 5, and 5+ based on the life history of black bears. And again, allowed a random effect for each age class, sex, and year, where we shared variances across sexes across years. We also then modeled harvest as effect of age class and sex again, with again a normally distributed random error with the variance shared across sexes. But importantly along this too is we also modeled harvest as a function of the number of permit sales across the state, where the idea here is that as permit sales increase, we would expect the number of bears harvested to also increase. But this relationship is not expected to be 1-to-1. And instead, we estimated that parameter to understand how the changes in the number of permits sold reflect back to the harvest probability. So keep this in mind, because I'm actually going to come back to this idea of how permit sales are related to harvest later when we talk about projecting into the future. Finally, for reproduction then, again, at the underlying process model, we can think about the number of cubs that are produced each year. And this is two-step process, the first being a binomial process of does the female have cubs? So we have some number of females in each age class and some probability that they are be able to produce cubs in that year. Here, age 0, 1, and 2 could not produce cubs. These black bear populations in this region start producing cubs at age 3. Then, conditional on having cubs, each female has some litter size associated with them. And this is what we're saying here is a 0 truncated Poisson with some rate of cubs per female. But since we already know this female has cubs, that's why we truncated that 0. So we modeled these processes then again as age dependent, where we allowed the age 3 to 5 and 5+ bears to have estimates of the probability of having cubs, and litter size also was allowed to vary between these two age classes. Then finally, we want to link this underlying process model back to the actual data that we have. And so what you're seeing here are harvested counts. So this H would be the count of the age class A, sex, management district, and year that are reported. And the number harvested then is some binomial function of survival and harvest out of the total number of individuals that are out there. So you can think about this abundance estimate being the abundance in January, how many survive to the fall, and then are harvested, and that's the estimated, that would be the number of bears we'd expect to be harvested in that case. Now, specific to this system, we actually had to add in 2 additional probabilities that we want to kind of pull out here. The first is this R sub T, which is the probability of harvest bears reported. So in the state of Maine, any bear that's legally harvested in the fall is supposed to be reported at a check station. And so then this check station records everything, and they mail the books back into the state at the end of the year. And all those processes have to occur for a bear to be reported as harvested. But then in addition to that, when they receive that information, they also then, for this age at harvest model, have to have a way to say, well, how old was that bear also? We found that the number of bears reported, that some bears didn't always have that age information with them. And so this theta sub T is the probability that a reported bear was actually assigned an age class when it was harvested. And so for the first round through this, we're going to go through, and we made the assumption that the reporting rate is 1, that we expect all harvested bears to be reported and then into the database. And then this theta T, we're actually able to estimate directly from the idea of the total number of bears that were reported as harvested and the number of bears that actually had age information with them. And that kind of gives you an estimate then of what this theta T would be. And this became a very important parameter in this model because actually the reporting process changed through the years in Maine, where in the earlier years, 2008 through 2011, this reporting of age information and submitting of tooth was optional, and we were only getting about 30% of the bears being aged. But in later years, it became mandatory, and the proportion of aged individuals increased by to about 80 or 90%. So in the data set, it looks like there's a dramatic increase in the number of bears that were reported harvested with age. It was actually a function of this probability of age reported, not the total number that were harvested. With that being said, we built up this model in a Bayesian framework using JAGs, and we're able to directly estimate or derive these parameters. And everything I'll be showing here after for estimates will be medians with 95% credible intervals. So the first thing I'm just going to jump right into is looking at the data from the harvest and the estimated abundance. But what you're seeing here is the actual raw data of annual harvest statewide. Overall, there was about 3,000 bears being harvested each year across the entire state, with more males than females being harvested through time, but fairly consistent trends through time. You also notice, though, that the number of bears being harvested by management district is extremely variable across the state, with the largest number of bears being harvested primarily here in the north, east, and western sections, and very few bears being harvested here in the southwest. These are more of kind of the developed areas in the state, where each one of these different management districts generally had less than 10 individuals harvested in any given year. So scaling this up to our abundance estimates then, we're just going to jump right into it. What you're seeing now is the estimated abundance on the y-axis for the statewide estimates. The black dots are the total number of bears, the total estimated number of bears across the entire state. The red are the females and the blue are the males. A couple things to hopefully jump out at this. The total statewide estimate was about 15,000 individuals across the state. The average annual population growth rate was 0.99, suggesting the population was actually quite stable across this time period. You'll also notice that there's more females, the estimates of more females relative to males, which is exactly opposite of what we saw in the harvest data. So the fact that we were seeing more males in the harvest data was not a function of more males being out there. It was actually a susceptibility issue where more males, the proportion of males being harvested was higher than those of females. Breaking this down though and taking the statewide estimate and looking at more regional estimates, a couple really important trends started to pop out in that we can estimate about 15,000 individuals across the entire state, but the abundance of individuals by management districts is highly variable. So again, what you're seeing here on the left in this heat map is the estimated median number of bears in each one of these management districts. And again, you can see that there's higher numbers of bears in this north and eastern and western sections relative to the southwest section, with upwards of almost 14 to 1,500 bears in some of these areas. Through years 2008, 12, 16, and 20, you'll see there's not a dramatic change to the population, which again is directly linked to that idea of that population being relatively stable through time. If anything, there might be a slight decrease through here, as suggested in the previous slide, of a population growth rate of about 0.99. So the bear population, there's a chance it may have declined slightly in 2020 relative to 2008. Here on the right thing, you're seeing the posterior distributions of our estimated abundance for each one of these management districts in 2008. And you can see that it's kind of a very large distribution of abundances, range everywhere up around 13 to 1,400 bears, down to these management districts here of 20 through about 25, where the population was often estimated as less than 50 individuals in any one of those management districts. We can then translate this directly into bear density, or the bears per square kilometer, since we have the estimates of area for any one of these grid cells. And this becomes really interesting in that although abundance kind of had this large distribution across the different management districts, we now see the general population kind of fall, almost every management district fall into one of two categories, where we had this larger category here of management districts that the abundance was generally between 0.2 and 0.3. And then we had these other management districts that are here in the 20s that the density was oftentimes very close to zero. And there's only a few of these transitional management districts that have this in between kind of around 0.1 density estimates that are shown here kind of surrounding these areas. But again, this very high 0.2 to 0.3 density across large areas and fairly consistent across the state this way. Overall, this gives a statewide average density estimate of about 0.18. For reference, some of the other bear studies that have been going on looking at direct ways to estimate density from things like spatial capture recapture in nearby states in New York and Vermont have been getting estimates of about 0.2 to 0.3 also in some of those areas. So again, this overall average seems to be fairly consistent for bear populations in the region. Now, the underlying demographic parameters were the next step to try to think about what demographic rates were that were leading to this fairly stable population through time. And so we're first going to jump into survival. And what you see here is survival probability on your y-axis and our 5 different age classes here on your X, cubs, yearlings, 2-year-olds, 3 to 5, and greater than 5. The survival estimates are broken up into females being red and males being blue. And then our natural survival or non-harvest survival probability is shown as the open circles, and our total annual survival, which includes harvest, shown here in the filled circles. 2 big points I want you to walk away from this figure with is that in this system, the non-harvest or natural survival probabilities are much greater than the annual survival probabilities. This difference between these two is driven by the harvest rates. And so it really seems like harvest is a primary source of mortality in this system for black bears. The other thing that becomes apparent is that there's the annual survival, these filled-in circles, really varies between sexes and age classes. But overall, this female survival was slightly higher than males, and that seemed to be a fairly consistent trend throughout. And you'll notice that there's these big gaps between most of these age classes except for cubs, which goes back to the idea that cubs are very rarely show up in the harvest data, and they're actually very rarely harvested, suggesting that total natural survival is actually quite similar to the annual. We can then tease this apart even farther and look at annual variation by age class. So you're seeing a very similar figure as before, but now on the y-axis, survival probability of adults, females in red, males in blue again, annual estimates here in the field, and natural here on the top. And as we mentioned in the previous slide, where we said that the natural survival of bears is often, especially for adults, is extremely high relative to harvest probability. We see that similar approach here then in the annual estimates, where the annual estimates for these bears was oftentimes at 0.97 or even higher, your natural survival, but the overall annual survival is highly variable per year, much lower, of about 0.8 for females and 0.7 for males. And again, this difference is being driven by the harvest rates and variation in the harvest rates through the years. In terms of reproduction, we again tease this out into our age classes of age 5+ females versus 3 to 5 year olds, and a couple of things that really pop out in this figure. So on the left-hand side here, what you're seeing is the proportion of females in each age class that had cubs in each year. So in other words, what we're looking at here is about 50% of the females that are greater than 5 years old had cubs in any given year, where about 30% of the females that were age 3 to 5 would have cubs in any year. You can also see that there's a fairly strong dynamic process here of high, low, which is common of bear populations in northern latitudes here, where you'll get a pulse of cubs. Those cubs stay with the female for about 1.5 years, and then they leave, causing this cyclic pattern. It's interesting that it starts to dissipate here in later years, and no longer see that strong trend. Now, these age 5 and older individual females became pretty obvious how important they are to the population here. Because not only are they more likely to have cubs in any given year, when they do have cubs, they have more cubs than the younger females. So what you're seeing here on this axis here is the expected number of cubs per breeding female. So given she had cubs, what's the expected number? And you'll see that for the younger bears, the 3 to 5, the litter size was on average about 2 individuals, or for these older females, it was about 2.5. They're really showing that these older age classes are quite important to the stability of this population. Now that we've better understood the underlying demographic rates of this population and see how the age influences that, we can actually directly investigate the age structure of this population and look at how that changes through time. And so what you're seeing here on these figures is looking at the observed age structure on the left and the estimated level population age structure on the right. A couple of things I want to really point out here. You can see in that the actual harvest data, you have age or cubs here on the bottom, 1, 2, 3, 4, the whole way up to our age 10+ individuals. Along the bottom, then you can see that cubs very rarely are harvested. They make up a very small proportion of the observed age structure in the harvest data. However, cubs make a large proportion of the overall estimated population level age structure, which intuitively has to happen. You have to have this large juvenile age class to recruit into older age classes. The other really interesting thing that popped out here is that through time, the proportion of the oldest age class that was in the harvest data was actually declining through time till about 2016, and then it kind of leveled off. And we also see this in the estimated population level age structure, where it looks like the proportion of older individuals was larger in 2008 and declined through time. That trend in that decline of the oldest age structure was apparent in both males and females. This decline was evident as a smaller, older age class shown here on the top. Another thing that was pretty interesting in separating age class by sexes is also that older males make up a much smaller proportion of the male population than the older class females, which directly goes back to what we were seeing of males having lower annual survival, suggesting that they're less likely to survive to these older age classes. So one of the other things that comes about this then, and bringing those together, would be to say, well, we know that these oldest age classes females are highly important to the population, given those previous results of saying they're more likely to breed and will have larger litter sizes. So the next thing we were thinking about then is, if this population of older individuals, females, is actually slightly declining through time, are we seeing a reduction in the recruitment? And so what we could do then is we could actually go back and look at age-specific abundances to understand how the number of recruits is changing through time. And what we were able to find is that although the population age structure has slightly changed through time, this number of recruits shown here on the bottom, the number of cubs that are entering each year, is actually relatively consistent through time. Again, in the earlier years, we saw a little bit more of this reproductive synchrony where there's up, down, but then overall it kind of averaged out to be about 3,000 individuals being harvested in any given. So now that we had all these information on the idea of how many bears are out there and the demographic rates that are driving population change, we wanted to go back and talk about predicting responses to management actions. This goes back to the goals of black bear management the state of Maine has, which is written out in their wildlife management plan. It's talking about maintaining healthy populations, providing opportunities for the public to enjoy bears, and increasing public understanding of bear ecology. For the purpose of this project, we needed to then think about how we could turn this into quantifiable objectives that we could directly evaluate relative to their management program. So in working with the management agencies then, we identified this idea that we could translate this into an idea that one of the things we could think about would be maintaining the bear population from between about 10,000 to 18,000 individuals for the next 10 years. And how the management agency can help influence that would be going back to the idea of they can control the number of permits being sold. And for reference, during the period that we actually analyzed, the mean number of permits being sold across years was about 10,000 permits each year, ranging from just around 9,000 to upwards of 10,500. And that relationship between permit sales and harvest probability we found in the modeling approach did end up being positive and significant. Again, this is not a one-to-one relationship saying that for every permit being sold, another bear is harvested, but instead it suggests that there is a relationship there and there's uncertainty in that relationship. So then the next question was, well, if we want to predict going into the future, what are our permit sales going to be? So we can maintain the status quo at 10,000. We could decrease harvest rates to permit sales to about 9,000, or increase to 11 or 12,000 with the metrics that the state agency wanted to investigate. And we could then finally quantify our evaluation metric as the probability of the abundance in 2030 is between our lower and upper bounds. And so this is what it looks like when we predict it out. You can see here that these are, again, our estimates from our 2008 to 2020 data, getting about 15,000 bears per year. And then we project moving into the future with our 9,000 permits sold in red, 10,000 in black, 11,000 in light blue, or 12,000 permits being sold in dark blue. And overall, the probability of success, shown as the probability of staying between the lower bound, as the dashed line, and the upper dashed line here, was highest for maintaining the status quo of about 10,000 bears, which gives us about a 0.81 probability that the final population in 2030 remains between those two bounds. And then finally, taking this to the next step, we wanted to go back and think about some of the sensitivity to reporting rates. So as I mentioned before, some of the ways these data are collected at the statewide level are that when bears are harvested, they're reporting at a check station. That check station then has to report the information back to the state, and the state has to enter that information. And interestingly, during our study period of 2008 to 2020, some of that process had actually changed, particularly in 2012, where there's a change in personnel at the state, and also kind of some changes in how those books are being returned and entered into the system, which the management agent was very interested to know, well, what if something did go wrong here? How sensitive are these results to the possibility that we didn't record every bear that was harvested? And so we went back and they actually kind of outlined an almost kind of worst case scenario of what would the reporting rates actually be if kind of the worst case scenario happened during these periods. And for 2008 to 2011, I'm quite certain based on how everything was done that the reporting rates were 1 or extremely close to 1. Then during 2012 to 2017, when this change happened and how things were being reported, they were concerned that sometimes 1 to 300 bears could almost actually go missing or not be finally entered in the database, which gave us a reporting rate of about 0.9, still actually extremely high reporting rates. And then 2018 to 2019, they changed to an electronic registration. And they think that would have increased their reporting rates relative to the previous years, but still possibly been slightly less than 1. And so what we want to do then is to take this and go back and refit the model using these reporting rates to see if it changed any of the inferences that we can draw from the overall And so what you're seeing here now, again, is our abundance of bears, estimated abundance of bears on the y-axis. The previous estimates that we've been doing with the reporting rate equal to 1 are shown here in the gray, and the new estimates that are using the reporting rates less than 1, particularly this one shown up here, are shown in black. So two things really pop out at you on this one is that, in fact, by accounting for this possibility of lower reporting rates does increase the estimated abundance of the population across time. However, it doesn't really change the overall take-home message of a stable population during this time period. So although we can change the reporting rates and even change the reporting rates through years, our main take-home message is that the population still appears relatively stable from 2008 to 2020. And just to verify that then, we refit the entire projection model looking at our probability of management success moving forward to 2030 under these different reporting rates, and the overall take-home message kind of remained the same. This idea of maintaining the status quo with about 10,000 permits being sold per year still gives you the highest probability of success for this management program. So really in the end, this really kind of helped us sleep a little better at night with the idea that even under the kind of the worst case scenario, things that could go wrong with our reporting rates, it still seems like the same management objective moving forward would give a high probability of success. So overall, bringing this back together then, kind of a summary of what we're able to figure out with these approaches is that these integrated research and monitoring programs using this age and harvest data are really flexible and provide really important ways that we can think about using relatively inexpensive statewide data and linking that to more emphasized research information that can give us the estimates of demographic rates. It's nice to see that this data integration approach also probably reduces some biases in any one data sets. So we can think about there may be some of the reporting rate biases that are creeping into the harvest data. And since we have the underlying information on survival and reproduction coming from a separate data source, it can actually kind of help reduce some of those biases that may creep into any single one. Overall, it appears that this Maine black bear population was relatively stable from 2008 to 2020, but that harvest was the primary source of mortality for these. It looks like permit sales are directly linked to changes in population trajectory. So the state does have a way that they can think about how they can manage and conserve this bear population in bounds that they would be interested in under their current management strategies. And more broadly, stepping back then to really fun ways that we can think about how these recent advancements in integrating age, capture, recapture, and count data can really be used across populations to address a lot of important applied and management questions in harvested and non-harvested species. We can think about ways that it can be used to improve parameter estimation, reduce biases, and investigate new and really exciting questions about how age structure and aging directly links back to population growth rates and population dynamics. And also, too, ways that we can think about how these approaches kind of really unify these concepts of population or projection matrices directly with demographic estimation studies and fully propagate the uncertainty to both make predictions and estimates of what's happening in these different managed populations. So with that, I really want to thank everybody for their time today. It's been a real pleasure being here and giving this talk. And if we have time, I'd be happy to take any kind of questions. My email is there also on the bottom, and I'd love to catch up with folks afterwards too. So thank you.
Awesome. Thank you so much, Nathan. That was a really cool talk. It's cool to see all the cute little cub photos too. So I appreciate it. All right, we have our first question. Let me, you should be able to see it, Nathan, but I will also read it out loud, and if needed, I might ask to unmute Stephanie. All right, sorry, I'm making this a little bigger too. So Stephanie says, thank you for the presentation, really cool work. Could there be additional mortality associated with killing a female bear because she had juveniles dependent on her, which are then orphaned, compared to harvesting a male bear, since it can be so difficult to determine the sex of black bears? So sorry if she missed this or if it's a silly question, because she's not a bear person.
Yes, Stephanie, that is a terrific question and an extremely observant point there. So that was actually a big challenge for us too, because the statewide harvest information that reported bears didn't have anything about their reproductive status with them. So it would just get reported of their age and their sex, but since they were harvested, we wouldn't know if cubs are with them. And you're exactly right that if this female here was harvested and she still had her 3 or 4 age 0 cubs with her, it could end up changing the survival probability of those subsequent cubs also. We weren't able to directly model that process, but it is a great point of this idea of harvesting a female that had age 0 cubs could lead to changes in survival process with this. I will also note that for this main population, there was historical where these age 0 cubs would always den with their mothers that first year. And they've seen a decline in actually of that recently, where these age 0 cubs now are able to put on a lot of weight in their first year, and that some of them are actually denning alone or becoming independent prior to their first denning season. So not only could it make that difference, but that difference may actually be changing through time, and it's currently not incorporated into the model. It's an excellent observant point. Thank you.
Cool, thanks, Stephanie. So Trevor asks, my apologies if I missed this, but could you use your model to predict a sustainable level of harvest?
Yes, we could in that way. So we could think about deriving or directly estimating population growth rates and fitting this back into the idea of saying that if the maximum growth rate was given for this population, then we could estimate what the sustainable harvest would be. We have not done that at this point, but I think we could actually go back in and figure that out with this population.
Cool, thanks. So Eli Holmes has a question. So great talk. So you might want to go back to some slides, be ready for this. Regarding the slide on the effect of different harvest levels on meeting population thresholds, Eli asks, are there plans to test these projections? For example, once harvest levels for a year are set, to test whether this harvest has the estimated impact on the population.
That is another great point. And so one of the points about building this integrated agent harvest model for the state agency also was the idea that they could find a way to integrate this large statewide source of information they have and continue to update that in the future. And so these 3 study sites are still continuing to be able to collect data for the market capture and reproductive data, and the statewide information will still be coming in. So in theory, we could, in about 3, 4, 5 years, whatever it may be, actually go in and see what the predictions from the current model would be for the data that'll be collected in 5 years. And right now, there is no underlying decision to actually test it or evaluate it that way, where you could actually alter the number of permits being sold to see the response in the population. But right now, the management agency is looking at the idea of saying, can we maintain the permits at about this level, which would give us the ability to go and say, well, this is what we predict should happen in 5 years, and then come back in 5 years and see what the actual estimate would be like. So if that's of interest, let's do this seminar again in 5 years and see what actually happens. That would be really fun.
All right, so Mark has a goodness of fit question. So great stuff, Nathan. It seems like the relationship between permit sales and harvest would have a big effect on the projections of alternative management strategies. So did you do any sensitivity analysis? Also, did you do any goodness of fit testing for that parameter? And were there any alternative approaches that you considered for modeling the relationship between permit sales and harvest?
Yeah, Mark, that's a great point. So a couple things I'll try to break this apart as. Did you do any sensitivity analyses? Short answer, no, not anything beyond that reporting rate challenge that we talked about there at the end, where the management agency was quite concerned about the idea of some of these numbers being slightly off. And if that was true, would that affect their overall inferences? So I'd love to go back and think about that one too. Goodness of fit testing, we did some goodness of fit testing for the individual data sets to verify that the known fate model and the reproductive data, so the survival and the reproductive data actually produced reasonable estimates using Bayesian p-values. And they did come back as adequate for goodness of fit in the individual analyses. Fitness of fit of some of these larger scale analyses are a little more challenging at times. So we didn't do it for the full model, but we investigated each individual model separately that way. And were there any alternative approaches that you considered for modeling the relationship between permit sales and harvest? Yes, this was a long discussion and an important discussion with the management agencies. Because one of the things about the way permits are being recorded right now is this idea that you have the total number of permits being sold per year across the state. But if you recall in some of the previous figures, there's a large difference in the number of bears that are harvested by management district. And we don't know how permit sales relate back to each specific management district. So the state permits could increase and look like they increase, but maybe it's all the hunters are going to one area and not going to another. And so this variable level of almost think about as effort per management district could be a really important piece of this puzzle to understand, especially when we're thinking about things of how the population may be changing in space and time through the years or expanding into areas. Would be really fun to go back. We've been talking about this with the management agency. Is there a way we can get these permit sales information to be at a management district level rather than just a statewide level? And we talked about ways we can build that into the model, but right now those data don't exist. But again, as part of this process was identifying critical information needs, and this idea of the spatial distribution of effort, or where these permit sales are actually going to be in terms of hunted in the management districts, is one of those things we're really trying to think about moving forward.
Cool, good questions, Mark. One question. All right, so Matt Farr, a new postdoc in the Converse Lab, said, "Hi Nate, great talk. Is there any interest in incorporating other metrics of hunter effort beyond permit sales, such as how bears are harvested, season length, permit holder, resident versus non-resident, etc.?"
Man, these are such great questions. Matt, it's great to see you again. Oh, kind of see you. So this is a really fun one to think about. And yes, it is, because going back, especially with this idea of the age structure being known under this, and how age structure then can be directly linked back to the population dynamics, it was really fun to see the managers then start thinking about, well, we can actually maybe direct the age structure of harvest by allowing for different types of harvest to occur. In Maine, there's allowed for baiting, and it can actually affect the ages that come in and be harvested. And so, as was pointed out earlier, it's a little hard to tell if you're harvesting a male or female sometimes per se, or the age class of it, but different methods could lead to different ages being harvested. And that would be a really fun thing to think about. So it's just beyond permit sales, but it's the type of hunting that's been done. The other fun one that would be a smaller model pointing out some of this information and really looking at call-specific mortality. So bears that are harvested, what type of part of the season are they harvested in, how are they harvested, harvest relative to other sources of mortality. There were a handful of bears recorded as being killed from car collisions. And so getting more into those kind of smaller analyses to investigate specific questions like this would be really fun as a next step.
Cool, thanks, Matt. I have a quick question. This kind of goes along the lines of what Matt just asked, but I'm wondering what sort of environmental covariates you would want to add into your models. Because I imagine, like, I don't know, the spring melt, like snow melt, might make a huge difference in bear survival rates. Yeah.
So duration of the winter season can be a little bit like that, like when you go into the den and then when you come out. So how long do you spend in a hibernation period, and then the condition that you're in when you come out. For things that we can think about changing through time, food availability is a real big one. We don't have it here right now. So years with larger masts of acorn crops, natural versus farmland foods, those kind of things. Unfortunately, there wasn't a really good quality data set that covered the entire temporal period that we're interested in, but it'd really be fun to try to think about why some of those things are varying through time. And again, with harvest being a primary source of mortality for this population, it was really interesting to talk to the folks in the area, but they're saying in years with poor harvest, it's not that the bears have a lower natural survival probability. It's that they're being pulled more into these baited areas for traps, as you actually see harvest go up in years with poor food quality. And so there's this relationship between survival, food quality, and harvest that are all kind of interconnected there. And so getting more information on this underlying food availability would be really exciting. And then when we think about year one abundances too, trying to understand what's causing that large variation across the state into year one densities, where we had this very low density in those more urbanized or developed areas, more consistent density across the rest of the state. Trying to link that back to percent forest or some kind of human density or anything like that. Are all things we'd really like to think about more, but just currently didn't have the data sets either spatially or temporally to cover them.
For sure, cool. So it seems like we don't have any more questions, but thank you so much, Nathan, for your time and for sharing your research with us. It was really great to hear from you.
Thank you, everybody. I really appreciate it.
Awesome. And as a reminder, we're meeting again next week, and we'll be hearing from Lily. So thanks, everyone, and have a great weekend.